the next speaker is the last speaker, İskender Yalçınkaya from Czech Technical University, and he will talk about disorder-free localization in quantum walk. And please, İskender.
Thank you. Thank you for your kind introduction. I hope you can hear me and you can see my screen. I know it's full-sized.
Okay.
Yeah, thanks for your introduction. I would also like to thank the organizers for giving me this opportunity to speak in this workshop again. In my talk, I will tell you about one of our recent works, which published recently, actually here. It has the same title as my talk. It is disorder-free localization in quantum walks. To be honest, since our ideas took a lot of time to mature, our paper involved many ideas, as you can see here, but I'm not going to talk about all of them. I'll just follow this safe trajectory. I'll first introduce quantum walks from a conventional point of view. And then I'll describe quantum walks interacting with a spin environment, which is actually our model we considered in this job, in this paper. And then I'll directly jump into some of our results about localization without explaining any mechanisms behind them, because these localizations are regarded as disorder-free localization in literature. But before I come to there, I need to tell you about disorder in quantum walks, some disorder schemes in quantum walks. And then I'll describe why we obtain these localization effects. And if I have some time, I'll tell you about how our work is related with many-body localization from the point of view of this spin chain. These are my collaborators. I also would like to thank each of them sincerely for their cooperation during this study. What are quantum walks? They were introduced almost 30 years ago as the quantum counterpart of classical walks. They are called counterpart because a quantum walker takes a step in the same way a classical walker does. We first toss a coin, then we move the particle according to the coin state. But since we are talking about quantum mechanics now, our coin state, our coin is a two-dimensional quantum system. And our coin toss operation is actually a unitary operation, I wrote down here. And the coin operator directly acts on the coin space. It simply rotates it simply rotates the state of the coin about the x-axis by an angle of theta, and we chose theta pi/4 in our work, and it doesn't touch to the position space at all. And then we move our walker according to the coin state. If we have a 0 state, we move the quantum walker to right. If we have 1, we move the quantum walker to left. And we repeat these actions, these two subsequent actions, and we call both of them as a step. We first apply a coin operation, which acts on the coin space, and then we shift the position of walker according to the coin state. This W defines a step of the quantum walker. So starting from an initial state, after the application of, say, 100 times, if we apply this coin step operator 100 times, this is the probability distribution we get, indicated by blue line here. And I also drew this probability distribution of a classical walker just for a reference. Quantum walk spreads quadratically faster than classical random walk, and this is advantages in some search algorithms and so on. So what do we have in addition in our model? We have exactly the same quantum walk model, but now we associate spin 1 over 2 particles with sites in our space. So in each position, we also have a spin 1 over 2 particle, or a qubit in a general sense. So after we take a step by C and T, by coin operation and translation operator, then our walker interacts with the particles, with the spin 1 over 2 particles at that particular position sites. And the nature of this interaction is the quantum walker just rotates these particles around about x-axis by an angle of phi. Okay, and we call this parameter as our interaction parameter. And it can take values from 0 to pi, and I'll describe its importance in a bit. Is there anything that I skipped here? Of course, we iterate this. Now our step operator has become Wm with an interaction with the spin chain or with the spins at every position. And we iterate this step operator again and again to govern the dynamics of our quantum walk, our model. So what do we obtain with this scheme, with this quantum walk scheme interacting with a spin chain? This is the energy diagram. This is the quasi-energy diagram of our step operator. And these are the quasi-energies, and this is our interaction parameter. The quasi-energies are 2 pi periodic because of the discrete nature of the step operator. It's similar to quasi-momentum. If we have a discrete space, then we obtain quasi-momentum, and in this case we have a discrete time evolution operator, and that's why we are getting a 2 pi periodic energy diagram. And if there is no interaction, we obtain all our eigenstates delocalized. By the way, and these colors represents inverse participation ratio of the particular eigenstates. So if the inverse participation ratio 0, then we have a complete localized state. If it's 1, we have a delocalized state. It's uniformly distributed along the lattice. If we have no interaction and we turn back, we obtain the conventional quantum walk. And this is the energy diagram of a conventional quantum walk. All eigenstates are delocalized. As we increase the interaction parameter, we see that these band gaps start to close, and they are completely closed at this particular phi interaction parameter value, 1 over 4. And then we saw that almost all of the eigenstates are localized. Of course, we obtained this diagram for 18 spins, for an 18-dimensional position space accordingly, and with periodic boundary conditions. And we solved, actually, we solved this step operator exactly. I mean, I obtained the spectrum exactly. And is there anything? We also, I would like to indicate that all delocalized states are gathered around the band gaps. So we see a localization, and these are some of our other results. And this is the probability distribution of the quantum walker on the position space after 400 steps. If if phi is 0, we obtain this conic distribution, probability distribution of quantum Walker. And as we increase the interaction strength, we started to get more and more localized probability distribution. And after we pass this 1/4 threshold, our probability distribution is exponentially localized. And this is the variance of the probability distribution with respect to number of steps. Again, we see that first a ballistic behavior. It's the signature spreading behavior of quantum walks. It spreads, its variance changes with respect to time with this, it's ballistically. And as we increase the interaction parameter, and we see that this spreading starts to stop. And after 1/4, after phi 1/4, we completely get actually sub-diffusive behavior of sub-diffusive spreading of our quantum Walker. And this is the inverse participation ratio values with respect to interaction parameter. Again, we see that our particle is localized after 1/4. And this is just another representation of the change of variance with respect to the interaction parameter. Again, the variance drops drastically after that threshold of our interaction parameter. Well, I explained we obtained some localized results if we consider such a model, but I didn't explain why do we get it. Before I come to that, let me just talk a bit about disorder models in quantum walks. Actually, there are a zoo of different disorder models in quantum walks, for quantum walks in literature, and I'll tell you about only one of them, which we studied earlier. And they can introduce disorder to quantum walks by just preventing quantum walk to go to a site. It's called broken links, and they can introduce it by just defining a different coin operator for each step, or they can also define it by just assigning a different coin operator for each position. But in general, we can classify all these disorder models into two categories. They either break temporal symmetry or position symmetry, translational symmetry. If we consider our first case here, this is completely temporal and positional transitional symmetric. We always apply the same step operator in each step, and particle doesn't coincide with something different in different positions. If they break the symmetry, then they obtain kind of disorders or bound states. And that's what we obtained in this paper. This is probably the simplest disorder model for quantum walks. Again, we have the same quantum walk model, but we apply the coin operator, translational operator. Then we put some phase to the quantum walker if it steps on the origin. In each time it steps on the origin. Okay. Whenever it's, I think I did a mistake here, but this should be, I mean, this is different than 0 if n is 0, and it is 0 for this. Yeah, I forgot to write that, sorry. So quantum walker gains a phase whenever it steps on the origin. In this case, and this is the phase obtained by the quantum walker, I indicated with E2I psi. And this is the position space, and the colors indicate the probability of finding the walker at that particular position, and this is this psi parameter in the vertical axis. We see that for most of the values of the psi, the quantum Walker is localized at the origin mostly, but it also has some distribution. It has some, it spreads. I mean, we see some bound states at the origin, but some eigenstates are still able to distribute, spread among the lattice.
İskender hocam, time is up actually. Could you please?
Okay, let me just explain what's happening in 2 minutes. Is that okay?
5 more minutes you can.
Oh, I have 5 minutes.
No, actually, time is up, but you can 5 minutes.
Okay. I'll this was my last slide, and so why do we obtain these localization results? Let me explain it lastly. Assume that we start from an initial state, and this represents the coin state, and this represents the position state, and this represents the state of the spin chain. And let's assume that we start from this particular state. Okay, an eigenvalue of z, Pauli z operator. And we can write this spin chain state in terms of plus and minus. I mean, the eigenstates of X operator in this way. So we can write the whole state as a superposition of 2 to n possible spin sectors. Okay. So whenever we apply, because we apply the coin operator, it only affects the coin space. We apply the translation operator, it only affects the position space depending on the coin state. And then we apply our rotation operator, the interaction operator M. And watch that, note that this operator affects these states separately. I mean, it affects the spin sectors separately, independent from each other. So each spin sector evolves in its own. In a way that whenever we apply this M operator in this sector, for example, or let's say in this sector, the quantum Walker possesses a phase of e to minus e phi. And also for this sector, it receives a phase of minus e to I minus phi and e to plus phi phase. So each spin sector evolves in its own disorder scheme, as I already pointed out here. So which means that we can block diagonalize the step operator with 2 to n blocks, and we have 2n and 2n blocks, and we have 2 to n possible blocks like this. And each of these blocks evolve the quantum walk in its own sector with its own disorder scheme. And we can see that if we want to calculate the probability distribution of the Walker on the position space, we see that it's equivalent to taking an average over all possible disorders we see here. And so the probability of finding the Walker at a particular position at time t becomes an average of all possible disorder schemes we obtain in these sectors. So that's why we obtain a localization as we did here in this slide. But of course, now we have a more complex and the localization of our part, the dynamics of localization of our particle is more rich. So I'll skip this slide. Here we also considered the dynamics of spin chain, and we saw some signs of many-body localized phase if we calculate the von Neumann entropy of the spin chain, so the half of the spin chain, but I don't have enough time to represent them. These are our techniques. Well, I don't need to talk about them too. So thanks for attention. I already exceeded my time. So thanks for your attention and for your understanding.
Thank you for your talk, İskender. And I would, on the behalf of the organizing committee, I would like to thank all the speakers in this section that they contributed to the quantum optic meeting. So our last session will be started at 4 p.m. So reconnect please at 4 p.m. Is there anything I need to specify, Ceyhun Hoca? Oh, is there any questions? So one more questions. One more question. İskender, are these conclusions beyond QW and extends to continuous works too? Are these conclusions beyond quantum work and extends to continuous works too? From
Are results applicable to continuous time quantum works? Is that the question?
Yes.
Well, I did I understand it correctly?
Yes.
Well, to be honest, I have no idea because I didn't make any calculation in that direction. So I don't know, but continuous time quantum works don't have any coin state, and our technique, our model takes its power from this coin state, and I'm not sure how to apply this model for continuous time case. Actually, I can't see it in the first place, but maybe there should be some way to do it, and we can define another model, or we can do some trick to. But our model takes advantage of these coin states, and that's why we get these, in some sense, get these localized results. And I don't know what would happen in continuous time case. I hope this answered your question.
Yeah, I hope so. One more question. Another subsystem can play the role of the coin. From Özgür Müstecaplıoğlu, Professor Özgür Müstecaplıoğlu, I guess. Thanks.
Oh, is this a comment or question?
Your comment, yes, comment, I guess.
Another subspace could play the role of the coin state.
Yes.
For the continuous time case, or for I couldn't quite get the comment, but can I see them here?
You can see it in the chat platform.
Well, somehow I can't see it. Where is the chat? But maybe if I stop my sharing, I can. Now I can see it. Yes. Are these conclusions beyond quantum works and extends to quantum from Özgür Hoca, and another subsystem can play the role of the coin? Oh yeah. Okay, now I got it. Yeah. So the second one is just a comment.
One more question from Theodora. Please, Theodora.
Sorry, I don't know much about quantum works, but can you use your model for describing like natural processes like photosynthesis or transfer of some energy and charge?
Quantum works are widely used to describe this kind of phenomena, especially the photosynthesis process, and they use both continuous time works and discrete time quantum works for that purpose. As far as
Okay, thank you.
You're welcome.
Okay, so thank you again. I would like to thank all speakers in this section for their contribution to the quantum meetings. So our last session will be started at 4 p.m. and please reconnect at 4 p.m.